Hello everybody, my name is Utkarsh Dwivedi and I'm presenting our work where we are exploring AI problem formulation with children via teachable machines. This work was a joint effort with graduate student Salma Elsayed-Ali and my advisors Elizabeth Bonsignore and Hernisa Kacorri. We are all researchers at the University of Maryland, College Park. Today, we are hoping to convince you that designing activities which engage children in AI problem formulation is a win-win situation. We can both advance children's AI literacies and we can help designers and developers better align children's values with AI and employ design metaphors that resonate with children. So, why is problem formulation so important? In 1938, Einstein and Einfeld told us that the formulation of a problem is often more essential than its solution. Fast forward to a century later, academics and practitioners consistently argue that mastering problem formulation remains relevant for AI. Obu Zakar advocates it to being as pivotal as learning programming was during the early days of computing. So, how would how might we involve children in AI problem formulation? In our work, we propose that one effective approach is machine teaching. Before providing you with some evidence for this statement, let me first give you an example of what we mean by machine teaching. Let's say we want a machine, it could be a phone or laptop, to distinguish between these three types of origami: a dolphin, a dog, or a ghost. You then collect multiple examples for each to teach it to recognize them independently of how zoomed in or zoomed out they are or how they are in their orientation. In this context, Zhu and colleagues then define machine teaching as a method that involves a teacher who knows the true thresholds for separating these classes and designs an optimal training set for the learner to learn to classify. An example of an existing technology that employs this approach is the Google Teachable machine, first deployed in 2017. Our team has been exploring this machine teaching paradigm in the context of a museum with an app called I Am Groot. This presentation focuses on leveraging machine teaching to engage children in AI problem formulation, where children can storyboard their own teachable machines. It is important to note that prior to this session, children were already exposed to machine teaching. They had engaged with the Google Teachable machine, doing similar design activities as those documented in our earlier paper at VLSCC at 2021. And they had interacted with our teachable app called I Am Groot. In both of these activities, children had little control over the AI problem these technologies could solve, but they offered familiarity. To scaffold and surface children's ideas regarding potentially complex problem formulation of their teachable machine, we structured the big paper technique to employ a series of problem reduction heuristics surveyed by Vodkema in 1983. We included sections that listed key questions and explicit design considerations. Specifically, we included sections for breaking down the machine learning process into functional units, for example, inputs and outputs, and specifying the technology used. Children were called to imagine and draw scenarios of how the teachable machine works in real life. They explained how to train it, anticipating how and when their machines might make a mistake, and describing how their systems could recover from mistakes. The storyboard was used in a larger participatory design session that follows a cooperative inquiry approach. The session began with snacks and socializing for about 15 minutes. We then had a design warm-up where adults and children sat in a circle, answered a question of a day. This is called the circle time and took about 20 minutes. The main design activity with the storyboard took about 25 minutes, followed by a presentation where children shared their teachable machine designs with each other. This took 25 minutes. Finally, children went home and the session ended with a debrief by adults over another half an hour. We had 10 children participating in our study whose pseudonyms are reported in the results. The children were 8 to 13 years old. We tried to balance gender with 6 being boys and 4 being girls. The children's demographics reflect our effort to include more non-dominant youth that are historically underrepresented in STEM learning, for example, from non-white or immigrant backgrounds. In total, we attained 10 storyboards and over 3.6 hours of video recordings, more than 1.5 hours of audio recordings, and 3 sets of field notes. We first analyzed this data, looking for evidence that AI problem formulation activities, like the one in our study, can contribute to children's AI literacies. To do so, we identified the key aspects that characterize children's formulated AI problems for their teachable machines. And we connect this work with Long and Majorco, which was published at CHI 2020. Prior to the study, children were exposed to teachable machines with problems typically formulated as supervised machine learning tasks, specifically as three-way image classification. Yet, in this study, many of the children's designs deviate from this in their problem formulation. They often included multiple models for different functionalities. For example, Penny's machine is capable of both early fall detection via the sensor in the bracelet and collision detection via weight sensors in the mat detecting the presence of others. Some children suggested that they would teach by showing the correct way to do a task, a common AI problem called learning by demonstration. For example, Ed's robot would fold the clothes, which is an example of learning by demonstration, as he would teach it how to fold a shirt or pants differently from folding a sock. We were also surprised to see a high variation among the input types, with video being the most common. Others included images, speech and sensor data like accelerometer and pressure. More importantly, children often envision a state of constant data collection and monitoring, providing a ripe opportunity for discussions around security and privacy in AI. For example, Adrian's handy helper will always be monitoring Adrian and learning in an unsupervised fashion from him. We invite you to read our paper for more results on specific teaching strategies envisioned by the children, as well as the errors they foresaw and how they plan to address them. As a second step, we look into the design metaphors that resonate with children in their ideas of AI-infused technology. Here we build on Schneiderman's seminal work in human-centered AI that calls for a shift in perspective favoring greater human control. We explore how children relate to their machines by mapping their ideas to Schneiderman's 4 pairs of design metaphors. Let us zoom in into one of these pairs, what Schneiderman calls social robots versus active appliances. Social robots are humanoid, anthropomorphic, or android, robots that are based on human-like forms. In contrast, active appliances are appliances that can respond to a command or user-defined rules. Surprisingly, we find that majority of children, 8 out of 10, wanted active appliances and did not anthropomorphize their machines. Only 2 had human-like names like Claude and Mr. Crab, or human-like abilities like emotion recognition. For example, Ollie's light was an image recognition based desk light that was switched on if she clapped, and it recognized her face. When she was asked how she would fix the light if it did not switch on, she said, "I'll be like, here's a pillow, and keep on throwing things for an hour, and sacrifice myself and go on to switch on the lights. If it does not work, I'll get so mad I'll scream into my pillow." As a third step, we look into the personal values that children incorporate in their designs. Here we build on Rokish Value Survey as an analytical framework to examine the values reflected in children's designs. We found that instrumental values such as capability, logic, helpfulness, and responsibility were shared among all children as preferred modes of behaviors for their machines. These are values that capture preferred modes of behaviors. Obedience was also common. For example, Adrian's handy helper reflected the value of helpfulness, which means working for the welfare of others. He describes his robot security guard as he's handy and he's like a helper and he helps me with everything. Less frequent for self-control, courage, and cheerfulness. When it comes to terminal values, Rukish describes his preferred end states. We find that they were less present, with a comfortable life being the most prevalent. followed by family security, inner harmony, and an exciting life. For example, Penny wanted her safety bracelet to warn people to get off the mat. She describes the support the bracelet provides to the team. When someone is falling, it blows up the mat and tells people to get off the mat so the faller can fall on the mat. Penny's safety bracelet reflects the terminal values of an exciting life with all the exercise that cheerleading provides, and the terminal value of family security because she does not want anyone in her cheering leading team to get hurt. We see a unique opportunity to gain different perspectives of the design space of AI by combining design metaphors with value lenses. Here we use Sankey diagrams to illustrate how this relationship manifested in children's designs, where each flow line represents the strength of the link or affinity between the two. For example, we observe that children's ideas with control centers and telebots are related to human values of responsibility and obedience, and so if a robot is designed in contravention of the design space, say as an autonomous teammate, but one which fails to communicate that it is obedient to the human, we can expect such a system to fail because the user would not feel in control of the robot. In a nutshell, our work contributes a structured storyboard activity for AI problem formulation, empirical results on how children as young as 8 years old formulate AI problems, new insights on prevalent AI design metaphors among children that engage with teachable machines, empirical results on shared instrumental and terminal values reflected in children's designs of AI-infused technology, and novel analytical lenses in AI problem formulation, linking Schneiderman's design metaphors and Rukish's value survey. Coming back to this win-win promise, we see how insights from our work could contribute to future research with a broader population to advance AI literacies and align the development of AI-infused technology with users' values and design metaphors that resonate with them. And we have come to the end of this presentation. Thank you for your attention.